So we are not speaking of my adventures. We're not going to speak of my adventure. We're going to finish the proof of growth in SL2. So what did we do last time? We did two things, essentially. We gave the proof of escape. I will state which cases of when we will need escape. So in essence, whenever you have a set of generators in a group and you believe that you should not be stuck in a variety, or if you are not stuck in a variety forever, then you can get out of it quickly. We will see how it works in practice. And as for the dimensional estimate, I will remind you of what we proved. We proved a special case of the following. So let me state the most general statement known. So this is due to several people. The so-called dimensional estimate. So let G, it's an algebraic group, so a group over a field, be an almost simple. So by almost I just mean whatever you could mean by almost. You know, you can take tiny, you can get a quotient, or you can take a big subgroup. So it's basically simple. For example, SL2 is almost simple because PSL2 is simple. All right. Then there are constants depending only. Let me also state there's a subvariety V of G. So G is an algebraic group. So it is a variety and it is also a group, or rather its sets of points is a group. So there are CDK that depend only on deg of V and dim of G. So dim is the dimension as a variety, and what I mean by deg, or the degree arrow, it's really a vector. It encodes all the degree information about V. If V were irreducible, it would just be the degree and the dimension, but we can just define deg of V. Well, the formal way does not matter, but it's just the degree and dimension of each reducible component. Of V. You can multiply the degrees if you wish. All right, very well. But so there are CDK which depend only on these two very coarse algebraic geometric quantities, such that for any A in GK face, well, the usual conditions, which are more or less conventions. And we also have that either we could require, and in practice, in where we will, that A generates G of K, but we can get away with a softer requirement. So such that A is not contained in any. So asking that A generates G of K is the same thing as asking that A not be contained in any proper subgroup of G. So it is enough to require that it's not contained in any algebraic subgroup of bounded degree, basically. Yeah, I mean, you can any finite set that can be that does not generate G. You could try to you could attempt to make it be contained in some very exotic subgroup, but of degree. Sorry. Well, I'm just done stating the conditions. I haven't stated the conclusion yet. Yes.
Is it true that all subgroups of G of K is an algebraic subgroup?
It's a bit, well, here we're, if you, yeah, that's the point. If you're talking about finite things, if K is finite, then if you take an arbitrary subgroup, then there might be a very perverse way to make it into the points of an algebraic subgroup by picking an extremely artificial algebraic subgroup of extraordinarily high degree. So that's why I'm stating, so this condition would be almost vacuous if I were not requiring that. All that I'm asking is that it not be contained in a natural algebraic subgroup. Yeah. So if so for every A in J K, which, well, it could generate G of K, great, or it could you could just require that it not be contained in any natural algebraic subgroup. And what is the conclusion? The conclusion is that A intersection V is at most a constant C is 8 to K dim V, which, you know, a posteriori is what you would expect, more or less. It's a very nice dimensional estimate. It tells you that, so in particular, if A grows very slowly, if A to the K is not much larger than A, this is telling you that intersection of A intersection V is at most exactly as much as you would expect from the dimension of V. So intersection of A with a line, if A, all you're requiring basically, I mean, it looks complicated, but you're not requiring much. In particular, this is true if A is a set of generators. This is telling that if A is a set of generators that grows slowly, then the intersection with a line is going to be at most A to the 1 over the dimension of entire space, say, or 2 over the dimension if it's a plane rather than a line, and so on. All right, so let me just state, so this is the most general version. It's a so this appears, this got two rather different proofs, but, and both statements were very slightly weaker or more special than this, though in practice they were as strong as this. So this was proven at the same time by Briagrin-Tao and P-Versavo. So this has two sources. Well, on the one hand, for the case that where A is a subgroup, and it is here that this delicate phrasing really becomes important, and that's why I have used it here, even though in practice we just require that A be, if A generates G of K, then this is true. So that was done by Larsen Pink. So their preprint is from the 90s, really. And for A general, so A just a set, in particular a set that grows slowly, just a set. But, well, I was doing it for especially G and V. Well, this was myself. So 2005 is when I was working on SL2, and I continued on SL3, SLN, and so on. But there was a lot of casework, in fact, sometimes. But it's very nice that there is now such a very general statement. Okay, but we will need it only for a special case. So A generates SL2 of K, so this condition is true very easily. And we will do it for, yeah, in fact, even more specially, when you have G of K, and for as a variety with which we want to estimate the size of the intersect, no, the variety with which we're going to intersect A is going to be of the form, well, the conjugacy class of G bar. What does bar mean? It means Zariski closure. Well, what does Zariski closure mean? the risky closure is just, well, we would have to go back to that. It's the smallest, it's the minimal algebraic set containing something. But in fact, in the case of conjugacy classes, it's something quite simple, especially in SL2. So in SL2, this is something very simple. This just means that the set of all H that have the same trace. Yeah, in practice, this is what it means. For at least when the trace of G is not very special. No, elements G with trace 2 or minus 2 are a bit strange. And this is not the last time I will say that. Also, then we get, so what is the result in that special case? We get that A intersection CLG is of course at most A intersection closure of CLG, and so we get that this is at most a constant A to the K dim CL of G dim G. But we know that, so dim G is 3, and again for G regular semisimple. What does regular semisimple mean? In SLN it just means having n distinct eigenvalues. In SL2 it just means precisely what I was saying before. Trace, well, that the trace of G is not plus minus 2. So those traces, you see, all the things, the only things I'm eliminating are these things of this form, basically. So these are special, but everything else, most things are like this. So for G regular semisimple, you have that the dimension of the conjugacy class is in fact true. Yeah, it's just you're conjugate to things that have your same trace. So you're imposing one condition in a three-dimensional space. You have two dimensions left. All right. So what do we do with such a conclusion? So an upper bound is nice, but lower bounds are even nicer, right? They give you that things exist. But we can get this upper bound to get a lower bound on something else, because something we also did last time was the orbit stabilizer theorem. And as I think I already said, it's especially interesting when you apply it to the action of G on itself by conjugation. And we are going to apply it for G, an element of A to the L, and we get that A squared intersection C of G, well, this is just what we were doing last time, right? We are able to bound the intersection with C of G by A divided by the intersection with the class. It was a special case of orbit stabilizer, because C of G is a stabilizer and the conjugacy class is an orbit. And so, well, we combine these two. So, well, we apply it with A to the L plus 2 instead of A. We get that A squared intersection C of G is at least A KL plus 2 thirds. So this is star star. We're assuming very little about A, but in particular, if A grows slowly, this A over A to the 2 thirds will be roughly A to the 1 third. No? So we get, let me just state in state on the board what I have just said, that here's what we will be using. Let G be SL2, K field, A in G of K, generating G of K. Well, A of basic conventions So these are absolute constants, so these are really constants. Okay, so this is what we have proven. The proof is just by what we just had and Kronecker-Rouget, or really just Rouget, since it's a non-commutative case. Because of course we had that by Kronecker-Rouget, because this is the case, this is also the, so this is going to be A1 plus O of KL delta. No, the idea is that we're going to choose delta small, delta quite a bit smaller than 1 over KL, and so this is going to be quite small. But everybody agrees? So Rouget tells you that if this is true, then this is true. Now, if A cubed is small, then A to the KL plus 2 is also small. And so all I'm doing is I'm just plugging that into here. I'm dividing by that amount, which is only slightly bigger than A. So I get A over A to the 2/3, basically. So I get A to the 1/3 minus small mistake. All right, so this is good, you see. It was already nice to have upper bounds telling you that the intersection of a set A that grows slowly with a variety cannot be much bigger than what you would figure out from dimensions. But in fact, this is telling us that in some particular cases, in particular for the centralizer of something, the inverse is also true. Namely, the intersection of A with any C of J is bounded from below by what you would expect from the dimension. This 1/3 is what you would expect, because the dimension of the centralizer is 1, and the dimension of G is 3. Very well. All right, so before we go for the kill and really start proving growth in SL2, well, this is one of the basic, ever since 2005, this has been one of the basic steps. When I was working on this first, I knew that well, I could see I had got many elements that commuted with each other, many diagonal elements if you wish. You can diagonalize them all at the same time. And so it's more or less clear that your game has just become a lot simpler. But before we finish the game, let me give you the treatment for A large. So the A small is the hard case, really, of the additive combinatorics. But let me give you the case of A large. This will involve a bit of a change of gears, because we will be doing a bit of representation theory. So in fact, the case of A large, you could do it with your bare hands. You would get a somewhat uglier proof and a somewhat weaker result, though still good enough. What happens for A large is that if A is, say, larger than G to the 8/9, then you can show without too much difficulty that A to the 20, say, will be the entire group G. In fact, you don't need 20, you just need 3. And there's a rather elegant way to show this. That's due to Gauss-Nikolov fever, soon after my first paper. And this will also be a good opportunity to talk a bit about eigenvalues, because those things figure prominently in some applications of Gaussian groups that I hope we will have time to discuss at the end. I think no drawing is required. So I think I did define the Cayley graph, right? But let me remind you. So a graph consists of vertices and edges. The set of vertices will just be the set G, whereas the set of edges will be, so an edge is a pair of vertices, so the edges are of this form, and we will be assuming that A is equal to A inverse and E is A. So this will be a symmetric graph. We define a linear operator let me call it A for adjacency. Being adjacent means to be next to each other on functions f from G to C. We call this A plus. So AF of G is 1 over A FAG A in G. All right. So, well, I often have the simplifying assumption, but here there's a different kind of very good reason. So, because A is A inverse, what can I say about my operator big A, curly A? Because this set is symmetric, if you wish, my operator is?
The sum is the sum of
over neighbors. Yes, it's a sum over all A in A. Okay. Thank you. Yes, exactly. It's a symmetric operator. And what can you say about the spectrum of
what is symmetric operator?
It's basically if it's its own transpose.
Okay.
Yeah, in the final case, it's just a symmetric matrix.
Okay.
So, как это по-русски? Симметричный оператор. Since it's symmetric, so what can I say about the spectrum of a symmetric operator?
It's real.
Yes. So all the eigenvalues are real. So there is a highest eigenvalue, lambda 0, which just comes from 1. It's quite easy to convince yourself by an elementary argument that there's a highest eigenvalue. You cannot do better than that. This is associated to the constant eigenfunction. No. If you take f a constant function, then A just takes f to itself. So 1 is an eigenvalue. And it's not hard to show that all the other eigenvalues are no bigger than that.
Okay, now it's not analysis of group, but only analysis in graph. This, yes?
If you wish, it's you're just taking functions, arbitrary functions from G to C. They are not multiplicative or anything.
No, it's
Probably it will be more convenient to write that functions from V. V
from
Oh, sure.
a function on
from vertex side.
on a
If you
graph.
prefer, yes. So set of vertices V. All right.
You now see usual analysis on
That's
the
right.
graph. Okay.
That's right. Okay. So we also have. So by definition, every eigenspace of A is invariant under the action of G on the right. Yes? And if you just start multiplying the variable on the right here, you only have to multiply the variable on the right here. So if you shift F by the action of G on the right, then you're just shifting AF by the same element. No, so the eigenspaces have to be invariant. So each is a complex representation of G. But what do we know about complex representations of G? Well, for linear algebraic groups, we know something quite useful. There is this old proposition with Frobenius. So this is the end of the 19th century. Let G be SL2 FQ, Q odd. Then every non-trivial complex representation of G has dimension Q minus 1 over 2. Corollary. Well, we will not prove it. It's standard, and the proofs I know take a lot of time. But,
Is no one-dimensional characters?
Yeah, sure. No, there's the trivial representations.
Only
Of SL2, that's the only trivial one. Yes.
okay.
Yeah. So a corollary then is, since each of the eigenspaces is a complex representation, and since only the constant eigenfunctions give you the trivial representation, only the constant eigenfunction is not moved at all when you multiply it by G on the right, then you have that every eigenspace, except for that of lambda 0, every lambda G has multiplicity.
Excuse me, Harald.
Yes?
I don't understand. Yeah, I don't understand this.
Okay.
If you have SL2F2.
Yes.
Okay. Okay.
Ha. People foresee this. Okay, that's it. Thank you for explaining why we needed this technical requirement of Q odd. All right. So how does this help? So the trace. So there's this ancient trick, which is, one of the main things a trace of something is good for, that a trace can be expressed in two ways. You can express it essentially as the sum of the number of returns to the identity. Let me explain what I mean by that. And you can also express it as the sum of eigenvalues. And that's how the trace of a power of a matrix is particularly useful in that way. So a trace of A squared equals, on the one hand, 1 A squared times the number of lengths to paths of the form V in the KD graph. Is this more or less clear? So the adjacency matrix is basically taking G, so there's G, and here are all the neighbors, AG of G. So what is the trace counting? Yeah, so it's counting. So you can use as your, all right, to compute the trace, you can use as your basis of the space of functions just the functions that are 1 at a point and 0 otherwise. It's a valid basis. And so what is, if you take that as a basis, what are the diagonal elements you see for a squared? They are the number of, so you take this distribution, which is 1 here, and you're counting in how many ways can you go to a neighbor and then back. And this is just a factor from here. No, I see you nodding, oh, well, but in the wrong direction.
I don't understand what's wrote here.
On the last line?
Yeah, it says the number of lengths to, of paths of lengths 2.
Oh, yeah, it's obvious. Yes, it's obvious.
Okay. It's really obvious or not?
Yes, it's obvious.
Okay, Alisa? Oh, you're taking notes.
Yeah.
All right. No, it's just the same thing as usual. So the ancient trick that the trace of a matrix is the sum of the diagonal entries, and it will also be true that it's the sum of the eigenvalues, and this is true for a high power of the matrix as well, or for a small power, and we're going to compare the two. So this is the sum of the diagonal elements.
Well, maybe in the Frobenius theorem, maybe Q should be more than 5, no?
Just to be safe. Yeah, that rings a bell, maybe.
Because you should say that PSL2 is simple.
Yes, sure, okay, all right.
Yes, I understand that it's...
No, thank you, very well. I mean, for Q-bounded, everything we're going to try to do is trivial, so, yeah. But for other reasons, we want Q to be, but never mind that. Okay, very good. No, but it's a good point, because I have notes on that, and I have to need to correct them. All right, very well, so the trace of A squared is this, but it's also true that it's the sum of the squares of the eigenvalues. So the two quantities have to be the same. So, you know, on the one hand you have GA over A squared. Why? Because how many lengths to paths are there of this form? Well, there are G choices for V and A choices for W. That determines a path. V, W, V. And the sum of the eigenvalues is, of course, lambda G squared, G, which again is at least, well, the multiplicity of lambda 1 times lambda 1. That's simple. Pretty brutal, but it works. So lambda 1, we have shown, is at most the square root of G over A divided by Q minus 1 over 2. So this is useful because for A large, this is much smaller than lambda 0, which is just 1. No? And whenever you have that lambda 1 is quite a bit smaller than lambda 1, even if yes, it's just separated by a constant epsilon from lambda, if there is some separation between lambda 0 and lambda 1, some fixed separation, you say that we have a spectral gap. That's something that people care a great deal. So it's good to have spectral gaps. In particular, here you get a big spectral gap. What does a spectral gap mean in practice? Well, you see, you have these eigenfunctions, and there's the one eigenvalue that is 1, and all the other ones are smaller. So that means that if you apply the operator to have any function, any a number of times, everything except for the constant eigenfunction is going to decrease exponentially. So in a pretty small number of steps, you're going to make any function into the uniform function. That's not important here, but it's important to know in general. AKF converges to a constant function quickly, exponentially. In fact, here we have something a bit stronger. So we knew that a to the k for a large was going to give all of the group. Let me just say a G. Equals P alpha, P odd. Yeah, you can check 5 and 3 by hand in the following statement. AG, A inverse. I don't think, yeah, you don't need to assume that A generates G, A will generate G anyhow, and we're not using that. Assume that A is at least twice G to the 8 nines. Then the conclusion is A3 is all of G. Whereas, as I was saying, careless arguments that do not go through representation theory, or a very careless use of these, would give A to the k equals G. Yeah, so when I first wrote a paper about this, I just did something fairly brutal with my hands. But this is a more elegant argument. I think this is due to Gowers Nikolov paper. So I will just give you a sketch of the proof. You can read it out yourself. Suppose that there is a G in big G, where G is not in A3. So suppose the conclusion is false. Then what you get is that the inner product of I'm not sure I like, yeah, that's right. The operator A applied to the characteristic function of the set A, here 1A inverse, the inner product is 0. That's just a restatement of the fact that G is not in A3. And at the same time, a computation, which you can do yourselves, but based on that, this inner product is in fact, well, there's a contribution from the leading eigenvalue, plus here comes a contribution from lambda 1. And, well, this will contradict that for A bigger than this, as you can check. All right, so this does it for A large. Yes?
Is it probably from more general theorem about 3 sets?
Yes, they do have. You have read the paper. Oh no, or you're very clever.
I just seen the theorem, but I never read it proof.
Yeah, it can work for 3 more general sets. I think if you're looking for precise exponents, maybe the same set is a tiny bit better. But here, I think 3 different sets would work. We just have to be a bit careful. That's all. All right, now let's do A general. So, theorem. So this was something I proved in 05. This is a newer proof, what I will give you. It's more in the lines of... The original proof was quite hard to generalize to SL3 and to SLN and so on, so it was done step by step. There were several papers by different people, but I will give you a proof that generalizes without so much difficulty. And, well, let me assume Q is odd. It doesn't really matter, but really needed, but yes, you don't have problems at certain spots. Then either, so A generates G. So let G be SL2FQ, let A be, well, actually at first I could do only Q prime for that matter, but let A be a subset of G, and let A generate G. Then either A3 is much bigger than A to the 1 plus delta, or where delta and k are absolute constants. Well, and in fact, since so as was proven soon thereafter, k is just 3. We have given the proof for k equals 3. All right. The proof here is closer to that of Weber-Savoy, I would say, among all the contemporary things. How does the proof go? So we can assume that A is A inverse and A is bigger than a constant without loss of generality, because this is trivial for A constant. A cubed is always at least A plus 1. So we assume this without loss of generality. Is this short form familiar? Very good. By the escape lemma, there exists, so for any special form, for any variety, well, you can find elements outside the variety. In fact, in this case, it's something very simple. You have to avoid the elements with trace 2 or minus 2, the non-semi-simple elements. So that you can just do it in 2 steps, as I showed last time. It's a linear case. So there is an element that is regular semi-simple, meaning trace of G is not plus or minus 2. So let T be C of G0. Why T? Well, this is a so-called torus. Well, no need for quotation marks. So torus, a maximal torus, in fact. What is a maximal torus? Well, the name is a bit odd, but it basically means, in SLN it means just a set of the set of all diagonal matrices under some basis. You can think of the elements of T. You can think of T as being the group of the subgroup of diagonal matrices. That's true in some basis, not necessarily rational. Very well. All right. So in fact, well, literally, it's the points on the rational torus, on the maximal torus T. Let us not be pedantic. Very well. So I will give you some notation. Let me see. So we're going to have C of G of 0. We have already proven that there are many elements of A to the k in C of G0. Now, what are we going to do with them? The idea, well, we already saw before that injective maps are nice because their domain is not, their range is not any smaller than their domain. Their image is not any smaller than the domain. So they are a good way to get things to grow. We're going to try to build an injective map. The ideal thing would be to have the image in A cross T, say, and so to have the domain in A cross be A cross T, and then the image would have to be at least of the size of A times the size of T, or T intersection A. So of size A to the 4/3 or so. That would be very good. It's not going to be quite like that, but it's going to be good enough. So it's an inductive step, an inductive argument really, that will become clear at the end. So let me call something a pivot if it allows me to define an injective map. Which injective map? So call psi in G a pivot if the function phi chi going from a times t to g defined by a comma t gets taken to a psi t psi inverse. If this is injective, well, not quite the map itself, but when considered as a map, when you quotient out plus minus identity. So, all right, so okay, say there is a pivot psi in A. That's one possibility. What happens if there's a pivot in A? Then we are happy. Because since T is C of G0, we have already shown, as I was telling you, that the intersection of A with T is large. We showed at the beginning of today. Yep. So by the injectivity of phi psi, of that phi psi, a squared over t is going to be at least a times a squared over t divided by 4, because it's not completely injective. And this is, of course, a to the 4th 3 delta. Get no, yet we know by definition and by the fact that psi is in A that phi psi of A comma a squared over intersection t is contained in a to the 5. So a to the 5 is bigger than a to the 4 is 3 minus of delta. So we get a contradiction. Of course, setting delta smaller than a constant. No? 4 over 3 minus of delta is, in fact, so bigger than 1 plus of delta if delta is smaller than a constant. So nothing to do about that. We get a contradiction and we are happy. Very well. I mean, I'm stating it as an argument by contradiction, but it's just what I told you before. If the map is injective and it has, if its range, if its domain is A cross A squared over T, the size of the image is going to be at least A to the 4th third. All right. So, So there's another possibility, which is also not the most crucial one, I would say. There's a possibility that this can happen only if A is large, as it happens. There's a possibility that there exists pivots psi in G. That there exist no pivots. There are no pivots. Then for every psi in G, there exists A1, A2, A, T1, T2 in T, such that with A1, T1 being different from A2, T2, such that A1 psi, T1 psi inverse is plus minus A2 psi, T2 psi inverse, i.e. A2 inverse A1 is plus minus so all right. So we have, this is just our mapping equation, that A inverse A intersects every torus, basically. Yeah, that's, I mean, it can say that if for every xi the map is non-injective, that means that A inverse A intersects the conjugate of T by xi.
Is it all torus conjugate?
Sorry? All tori are conjugates in SL2, yes. All maximal tori, yes. It wouldn't matter if they weren't, because there would be enough size, but they are all conjugate, yes. So choose any. G then G is regular semi-simple. So yes, G not equal to plus minus C, and J is regular symbol semi-simple, and its centralizer equals, it's the same torus. So that's certainly true if it is regular semi-simple, and just the fact that if something is in a torus, and it's not the identity plus minus identity, the fact that that implies that it's regular semi-simple is something peculiar to SL2. In fact, it's the only step that in the proof here that does not work for SLN or for more general groups. And so you have to, but you can fix this. You can carry out the same basic argument for SLN. It's just that this step becomes more complicated. Very well. So there exist at least constant times a to the 1/3 minus O of delta elements So the same argument as always, you know. So there's lots of elements in C of G. Lots of elements of A squared. And this is true for every G. For every X. So I was saying. Now what happens, so you have these many elements on each torus, but there are lots of tori, lots of conjugates. They are all conjugates, but so there exists 1, 2, G of T, G over T, distinct tori. t psi inverse. And a given g, a g that is a semi-simple g, can be contained in at most one torus, but it's the same fact. It's contained at most, well, in fact, exactly one. So there's no double counting. So hence a of k is at least the sum of the its size is the sum of the intersections with all of these tori. Well, at least we are taking out the identity. So the number of tori so either you have that a cubed is bigger than e to 1 plus delta, in contradiction to what we are assuming, or a is bigger than g to the 1 minus of delta. But in this case, use Gauer's Nikolov-Piver, and you are done in just one step. A3 of all of g. Very well. We are left just with the most interesting step. Do people want a break, or should we go straight?
Yes.
A break. Very good.
Yes.
So, well, there's a third case where there are pivots and non-pivots in G. So, not everything is a non-pivot. You don't think it's B. There exist pivots, but not everything is a pivot, because if everything were a pivot, then there would be pivots in A. So, there are pivots and non-pivots. It's a very diverse world. And it's here that you will have the induction step, so to speak. It's a kind of induction. In the usual induction, you are using the fact that 1 generates the integers, the group of the integers. Here we're in a more general group. So, what are we really using? Well, since A generates G, this means, so it's not really an ordering, but we are still able to do induction, so to speak, because this means that there exists a xi in G and an A in A, such that xi is not a pivot, but a xi is. Agreed? Yeah, just pick any non-pivot and start multiplying it by elements of A. Eventually you will come to the point where you have an element xi that is not a pivot, but then a xi is. Otherwise everything would be a non-pivot. Change pivot to, I don't know, whatever you want, any property. Since xi is not a pivot, we have cross there. Alright, so we have that there are many elements of psi t, psi inverse in AK. No, psi is not a pivot implies by this that there is some element here, it is not identity, so the centralizer is psi t, psi inverse, and so you get many elements in it. But xi is a pivot, and so we're going to use that to get injectivity. And so the many elements here, we're going to put them in this injective map. We're going to get a lot of growth. It's injective, almost injective. Hence, hence we have phi xi we have ak this is going to be at least 1/4 yep, just by injectivity. This looks about right, yes? This is just the size of that. It's not changed by conjugation, obviously. That too, and this is injective. So of course, bars. All right. And as I was saying, this is big. So this is going to be 1/4 a 4/3 minus of delta. But we also have that this is inside ak plus 3, right? I mean, there's a spheric looking psi, but you're going to have conjugation by xi, so you're fine. So ak plus 3 is going to be, in fact, you know, I could have skipped all of these by contradiction. So at any rate, this contradicts further this small. All right, and so the theorem is proven. Now we can have, I mean, we have plenty of time. Well, it depends on when you have to go elsewhere, but for an informal discussion of some of these things, I think, so one reason people care about this growth theorem, so I gave you a reason last time that it implies small diameter of the Cayley graph, right? We went over that. In fact, it implies something stronger than small diameter. It implies so-called expansion. So, so there's this theorem by Morgan-Gambert, and it also generalizes to other groups. That's also non-trivial. It has been generalized by other people. And this is based on the theorem above. It's that you have, so let G be SL2. Oh, so it's now a Urey group again, and let A, let A0 be a subset of SL2 Z such that I think A0 better be Zariski dense in GQ, say. Well, so yes, say in G matters of language. In G. Just meaning that A0 is not, in practice this means that they are all not all, say, upper triangular matrices. This condition, the A0 is going to fail to generate something Zariski dense only when A0 is, say, a set of upper triangular matrices with zero or some conjugate thereof, with 0 downstairs and to the left. So it's a very soft condition. This just ensures, by the way, so this ensures that A0 mod P generates SL2 must be Z for P bigger than a constant. And this was proven by several people from the early 80s, Weisfeiler, Nori, and so on. They proved more general results. It's very convenient. But all right, so that's why this condition is here. Basically to ensure that A0 mod P generates SL2 Z mod be Z, though it helps in other ways. At any rate, you have these two conditions. So it's not going to be for an arbitrary A generating SL2 Z mod be Z. It's going to be for projections of A0 modulo P. Then you have that it's a family of expanders. What I mean by a family of expanders, let me define that. Meaning that there exists an epsilon such that for every P, the spectrum of gamma 0 modulo P satisfies lambda 1 minus lambda 0 bigger than epsilon. And this is stronger than just having logarithmic or polylogarithmic diameter. So I just remind you, I think I did say it last time, that with this theorem you can prove very easily that the diameter is at most log P to a power, completely uniformly. And in this situation you can prove without too much difficulty that the diameter is in fact at most log P times a constant. But this is a stronger statement. So I will give you a sketch of strategy, let me just call it a sketch of strategy of proof. It takes several pages. So this is not trivial at all. So if you just use my result as it is, then you don't get greater than or equal to epsilon, you get greater than or equal to 1 over log P cubed. Or if you're a bit smarter, 1 over log P squared. So I will tell you how to shave off each of these logs. So this will tell you about some ideas that are useful elsewhere. So first of all, you have this result, which is my result. And so the question is how to do each of these steps without losing something. For lambda non-special, so for lambda being, sorry, for mu, a probability distribution on G. So it's a measure of total measure 1. And if you assume that mu is non-special, then the convolution of mu with itself is flatter, that is, its L2 norm is smaller than just mu. Yeah. So you.
Mu is
an arbitrary. So mu is an arbitrary measure of total, such as mu of all of G is 1. Yes. Yeah. In fact, so it's very easy to go from here to here. You just look at the special case of mu, the characteristic function of a set A scaled down. But even for that special case, it's not so easy to go from here to here. In fact, that already, because to go from here to here, you use that for 1A, for the characteristic function, and then you apply Cauchy-Schwarz. But Cauchy-Schwarz is an inequality, not an equality. So you have to be careful when you go from here to there. And in particular, there's a tool that is important. It's the non-commutative version, due to several people, in a sense, Wu, Tao, and so on, of a theorem in additive combinatorics, the Balog-Gowers-Semeredi theorem, or Gowers-Balog. It's the Gowers' version of Balog-Semeredi. what does this theorem tell you? There are several ways to explain it. One way to explain it is that it's a sort of result that tells you that this implies that. It allows you to go from results and sets to results and measures in a very nice way. It allows you to say that if these were not true, then say that mu is 1a, it would not give you that this is false for a, it would give you this is false for some large subset a prime of a. It's a bit subtler. Okay, so once you have this, then you will already be able to get 1 over log p here. But you get another log, so you could get here lambda 1 minus lambda 0 bigger than c over log p. But in fact you get lambda 1 minus lambda 0 bigger than epsilon because of the multiplicity, basically. The same fact that we used before. The idea of using this in this context is actually already in sin XOE. Another paper. All right. So, so as I said, it's stronger than the easier consequence. Very good. All right, and things have developed since then. So as I said last time, these things have been generalized to well, SS3, SLN, and all of these groups. And you asked me a very good question during the interval. So as I also said yesterday, we have only weaker results for Siemens. I also said that, I think. Did I say it? Oh, so let me discuss a bit. So we have results of the type AAA for SLN, SP2N, SON, and so on. But delta depends on n, and delta must depend on n. So it's not just an artifact of the proofs, but you actually must have the delta. Delta is sometimes no bigger than 1 over n. Also false for Siemens. And these two facts are related because Siemens is basically SLN over the field with one element. The field with one element does not exist, but groups over the field with one element do exist. It's a bit like you were telling me, Alice, about Trintrabas, so the rabbits eat imaginary grass or something of the sort, but the rabbits do exist. Yeah, at any rate, Siemens is like that. Or field. Yeah, but you can prove. So I have a result which just appeared, but we proved it in several years ago, but it just appeared, which says that even though this result here, which implies small diameter quite easily, is false for Siemens, you can prove other weaker results of that kind and other results to complement them, so that you get that for G, Siemens or all 10, A in G, A generating G, the diameter, I did define the diameter last time, right? Did I define the diameter?
Yes.
Okay, so just a reminder, the diameter would be the least k such that G is A union A inverse. So the diameter of G with respect to A, we don't yet know that it is a power of log of the size of the group, but we do know that it is at most e to the log g to a constant. In fact, the constant is just 4, basically. So of course this means n, well, e to the log n to the 4th. It's really log n to the 4th times log n. So we have got that. So that's the best result known. So it is believed, even though this is not true for Siemens, it is believed that this is true for that we do have a bound that is polynomial. And it would be nice to get a dependence on n that would be this nice for groups, linear groups of unbounded rank. So this gives some hope that it can be done. So believed in general. As I was saying before, that it is simple, finite, non-abelian. So this is what we don't yet have. We have it for SLN for any fixed n, but we don't have it as n varies, and we don't quite have it for Siemens either. The diameter AG, A generating G, we have the diameter of G with respect to A is at most where the constants are absolute. What about non-simple groups, you may ask?
Everyone question now, and okay, as I understand them, this result about n in the O of 1 years,
yes,
is equivalent for SLN that delta.
No, but that would follow if the delta were constant independently, but delta is not constant. Delta does depend on n.
Yes.
In reality.
If we have delta equal 1 divided n.
Yes.
Then
you don't. No, that wouldn't be good enough. Delta equals, that would be very, very weak. It would not follow from, no. The delta equals to 1 over n, which is basically, yes, basically what you could get in Siemens. That would not be strong enough to give us that much, actually.
Yes.
Actually, no, you, wait. Yeah, that would be pretty weak. See? It would mean that a to the 3 to the n. But that's pretty darn weak. So yeah.
Okay, so that is for Sn we have that delta is 1 divided logarithm.
Yes, so sorry, for SLN.
Yeah,
1 over...
no.
Oh, for...
No, your conjecture for the group is...
The conjecture would follow if you had delta equals 1 over log n. Mm-hmm. But I think there may be there are counterexamples to that too. Mm-hmm. Sorry.
Mm-hmm. Okay.
I better double check, but I think that may be the case.
Okay. Mm-hmm.
Yeah, that makes sense because n in the symmetric group is the analog of the rank. And I do remember that in SLN there are cases with delta equals to 1 over n. Mm-hmm. Yeah. So, I mean, there are things that grow more slowly than 1 plus 1 over n.
What about solvable groups?
Solvable groups are a completely different kind of thing. I actually have a result on that. We finished the case of linear groups over FP. But it's a very messy proof. I think this has to be improved, and when it gets improved, it will naturally work over FQ. That's a result of myself and my former postdoc, Gil. So we basically reduce a solvable case to a nilpotent case. We show that in a solvable case, in a solvable group, if you have a set A, either A times A times A is bigger than A to the 1 plus delta, or you are in a very special case which reduces to a nilpotent case. A is basically sandwiched between two subgroups where the quotient is nilpotent. So it contains a smaller subgroup, or almost, and it is contained in a bigger subgroup, and the quotient of the two things is nilpotent.
Okay,
And an important case, you're about to ask?
yes, the important case, okay.
The important case is like the abelian case, it's Feynman, and we don't yet know polynomial Feynman. So you see, it's a very odd thing here, that in a sense the commutative case here is a case in which our results are still weakest, at least for n-bounded. Say in SL2, or in SL2, in SL2. In SL2 we get more growth than we do from Feynman. Because in SL2 the dependencies are polynomial, we get a polynomial result, so to speak.
Okay. No.
So morally speaking, yes.
And in a solvable group we have linear.
In the solvable group we also have that, as I said, that A cubed is bigger than A to the 1 plus delta, unless you're in a special case which reduces to a nilpotent case.
Okay.
It's something like this, basically. So, well, I don't know where to write. I'm using the blackboard as some sort of canvas now. But in solvable groups. So there are two statements here. So there's Nick, and qualitatively, so this is more general, but qualitatively it's very weak, in the sense that they don't get an exponent 1 plus delta. Again, it's for Green Tau in a later paper of theirs. That either A grows, meaning for us, the first paper, that A is bigger than A to the 1 plus delta, or there exists H1, H2 in G. So this is for subgroups of SLN FP. Such that I'm going to be very lazy and say basically that A is contained in H2, more or less, almost. And A to the K contains H1, and H1 is important. This is what Green Tau called the Helfgott-Lindenstrauss conjecture. I think we would, yeah, well, there was a guess at the time, and then we actually proved it. It's the right thing. But yeah, it tells you that if you're in an nilpotent case. So A is not necessarily contained in a nilpotent group, but A contains something such that when you quotient by that something, you get a nilpotent group. So it reduces to an nilpotent case, which we still don't, we don't have a result A times A cubed of size A to the 1 plus delta. That's not true in general in the nilpotent or in the nilpotent means, nilpotent is close to abelian. We don't have in the abelian case. Someday we will have a result of the form either A cubed is greater than or equal to the 1 plus delta, or A is a union of arithmetic progressions, but we don't have that yet because that would be polynomial Feynman-Ruja precisely.
And you don't have any
dependencies on the rank. Yes, the things depend on the rank. That's right. That's sort of K and delta depend on the rank. Yes. Yeah, here things depend on the rank as usual. Because remember all of those dependencies and degrees I mentioned, they depend on, yeah.
Okay. Can you explain it for the general group, for example?
Yeah, we also have a result like I think reducing it to the simple or the solvable case. Yeah, we have that in my. There's a there we create. I mean, we share credit for that chapter with Piper Sabo. Yes, we have a general result. But as I said, my paper with Nick, it's very general, but it's also a bit messy. In particular, the assumption that it's over FP comes from that. Of course, SLFQ can somehow be made to fit inside SLNFP for a larger n, but as I said, there's a dependency on n, so you don't want that. But yes, just look at my paper with Nick, with Gil. Ta-da. Are there other questions or other things you want to discuss in however much time you have left? Yeah, so this gives you an idea of where the field is right now. There was some sort of competition between several teams when it came to generalizing things from SL2 to SL3 to SLN and so on. But in the case of symmetric group, there hasn't just been so much activity as of late. Though for a while that seemed to be the case for SL2, but people were working in secret. So goodness knows, I hope we shall see.
And what about special?
Oh, that also, I was just lazy when I said SLN is, you mean all the exotic groups that are twisted and so on?
No, not about twisted, about, oh my god.
Oh, the special ones are fine too. And as for the monsters,
yes,
but who cares about them? There's a finite number of them. So these are asymptotic statements. We just make delta smaller. Make delta, they say that delta is 1 over the size of the monster. It's still going to be a positive constant.
Yes. Okay, because for the delta depends on for SLN depends on n.
Yeah, but
that's right. Absolute constant for all unsolvable.
Well, what I mean is for the special groups, this is fine. It's still a sensible statement because p varies, the field varies, and so on. The statement is non-empty. But for the monster, the statement is empty. That there exists a delta such that. Because you can just set delta to 1 over the size of the group.
Yes, because I would say that if the delta not depend on n for SLN, we would want absolute constant delta.
Yes, but it does. Yeah, that's really very nice, but it's not true. Yes.
Yes, yeah, that is true.
Yes, but for the monster group, it is an absolute constant. It's 1 over the size of the group. Yes. Are there other questions? Yeah, so I have tried to give you some sort of panorama. So the funny thing is that there's starting to be relations between the techniques I have talked about in the last 2 days with fields outside additive combinatorics. There are already some small points of contact with geometric group theory, say, but it's getting a bit farther away from the abelian case. And the ideas here have not really been used for the abelian case, and I don't know whether they can be. We shall see how things develop. And as for the middle third of the course, I really wanted to give you an idea of analytic number theory outside additive combinatorics, which is a special subfield. But also, there was an entire topic which deserves a course to itself, which is modular forms, which we did not do. That's extremely important, and that's in fact where half of all activity in analytic number theory lies. But that's a topic for a semester, 2 semesters, 4 semesters.
Yes, of course.
16, 30.
Here, question is if I have some group,
yes,
not solvable group, okay, and I want to take some proposition like this, what I should do if all proofs are special for special cases, yes?
Yeah, but nowadays it's not just, no, there is a general proof for all linear groups. It's just that the bounds depend on n, on the rank.
Okay, so it's dependent on, but
Yeah,
we can't now prove it.
Yeah, I mean, for the well-being, people are happy enough. There's a general proof that with bounds depend on n. Yes, it would be nice to have a different proof where things don't depend on n, but it seems fairly hard. As soon as you have algebraic geometry, you have the degree, you have dependence on the degree, and the degree is going to depend on the dimension.
No, I think we should take algebraic geometries and a specialist for algebraic groups, and he.
We need a different route because, as I said, the delta here is a feature of reality. Yes. So I hope that some of the ideas that I put forward for Siemens will be useful for removing the rank dependency in SLN, but we shall see. You're welcome to work on it. Well, in that case, we probably should call it a day. We're 5 minutes before the time, but we can do that. But do you have any other more general questions about the course, about what I think, about main areas in analytic number theory? If we're in the last day of the course, we can talk about all of those things.
2 questions. The first question is, I know that some students want to take an exam.
I heard about one student who wanted to take an exam.
Yes, and then yes, I understand you don't want to give an experience about university bureaucracy.
Sorry?
University bureaucracy.
Yeah, it's going to be a small nightmare, and I also don't. It's very difficult to. How do you examine one student? I mean.
It's
the same procedure as for 5 students.
Yeah, but what sense does it make? Oh, he's better than the rest. Yeah, the rest is in the empty set.
Never compare with the rest.
No, it's a rational system. Really, you don't know compare.
Yeah, but it's the first time this course is being taught. I have no idea, no way to calibrate the grade.
It was the same in Stiklov with Maxim's courses.
Yeah, I have no idea of how to give a fair exam.
Yeah, I think that first you should write a program of your course.
Yes, it's written.
I can give you some example how it usually happens.
Look, if this is something I have to do for the student and it's just a formality, and it's not, and it's something that I can actually do without spending millions and millions of hours on it, then I'm more than willing to make the student a favor. It's just that it's not going to be. It's just going to be a fiction. I shouldn't do this because I'm being recorded. But it doesn't make any sense as an exam. As in, it's just going to be. It would be nicer perhaps if he wrote an essay or something, or he wrote a small, a short expository paper. Do they accept that too, or not? Is it an option? Okay, so he really needs an exam?
No.
Oh, okay then.
No, but it would be good if you write a program of your course.
There is a program of my course.
No, it's a course. It's a program. It's a piece of paper. Then
it's like table of contents.
I did that at the beginning, and I almost followed it.
Yes, you have it, I guess, in the very annotation. There are something like 4 different parts.
Well, 3 parts. At the end, I made it shorter.
No, it will be better if this program will be not a 10 item, but 20 item. No, it's okay.
I can put in more. Yeah, I could just add more keywords. Yes, and say what I actually did, which is pretty much what I said. When I proposed the course, it was 4, then it became 3 with some sub. I could just write a longer description. Sure.
Yeah, and if one day one student will want to speak about this exam, we have a program.
So if he does not take an exam, so how is the abstract going to help?
If one student will want to take this exam, okay.
Oh, so you mean that a few years on the road he might be asked where
not yes, okay. So in January, of course, because.
So the student will know in January whether he really needs to pass an exam.
Yes, it works like this because in January we have a period of session. But whether it would be possible, I mean, in the sense of documents to pass.
Oh, it's documents. It's not your problem. Documents.
So what should I do? Should I? So you just write a longer abstract.
Yes.
Okay, and the student will hopefully choose not to take an exam, so he will never need to write exam.
What do you mean by to write exam?
So
you mean to write some problems.
That's right. Because where is he going to take it? I'm not going to be here. Or is it going to be a take-home or what?
No.
I did 1 year of studies like this.
No, in Russia exam of a special course, it's not solve problems. It's speak about this theory.
Oh, so he would give a talk or what?
Yes, in general, at least in Siklov, it worked like this. I had a
and
table of contents more or less like this, and Maxim gave me the topic. I prepared this topic, and I gave a talk on this topic.
Very well. So
that's why I was the only one.
It's a seminar, not course.
Yeah.
Very well. So
it's
and
the same.
who will be here? And it would be something that he has seen in the course.
Yes, it usually was like this for me.
And who is going to be here to hear him speak?
Okay,
very well.
It's not a problem.
Very well. Okay, so I have this list of contents somewhere. I can just write a longer. I can show it to you right now, and you can tell me where to put more things.
I can show you where to put more.
Okay. All right.